Well, good afternoon, everybody. It is the 27th of March, and I'm still in Washington. Actually headed to the University of Virginia tomorrow. Well, actually tonight to give a talk there, and heading back to Norman on Saturday morning. So if you have any questions, as always, please send me an email. If you have any questions about the problem sets, your term project first drafts are due here, I believe, April 1st or thereabouts. I don't have the date right in front of me, and I will quickly get those back to you in terms of doing your peer reviews. We will have another problem set, part B, coming up probably fairly soon after you finish problem set number 1. But it, again, will be rather short. It'll focus on storm dynamics, rotation, hodographs, and helicity and things like that. So ought to be kind of a fun problem set for you to work in terms of the kinds of things that are very interesting as far as the deep convection and thunderstorms go. Once we finish this topic of supercell storms, then we're going to move into tornado dynamics. We will talk about that and try to spend some time on hurricanes as well before we finish the semester out. Just remember that the final exam, which is actually just the last exam, the third hour exam, is on the last day of class, which I believe is Thursday, May 1st. I have to go back and look at that. But anyway, it's announced on the web, so just kind of be mindful of that. Remember, we left off Tuesday talking about hodographs. We were looking at various things you could do with hodographs, various quantities that you could determine by using them. We'd already done the shear vector at a given altitude, the shear vector between two altitudes, and also the horizontal vorticity vector. So what we want to look at now is the storm relative wind vector, which again is a very, very important quantity, especially when combined with the other ones that I just mentioned in terms of determining properties of updraft, rotation, and so on. Like those other quantities that we looked at on Tuesday, determining the storm relative winds is just a very, very easy thing to do on a hodograph. I think you can see from the, remember from that railroad car example I gave, and even the examples of storm relative winds in various storm scenarios, it's kind of complicated to have to remember. Storm relative wind is the absolute wind minus the velocity of the coordinate system. When you use a hodograph, it's very easy to do. You don't have to even remember that. Okay. So we can determine the storm relative winds very, very easily, but we have to have one quantity on the hodograph that I've not shown you yet, and that is storm motion. Okay, so we have the winds at all the altitudes, we have the hodograph curve, and then to get the storm motion, we either look at actual storm motion based on radar pictures or whatever, or we just make an estimate of what the storm motion is. But the bottom line is, once we have storm motion, we can very easily determine the storm relative winds. So for example, here's a hodograph. Surface winds 1, 2, 3 kilometers. And by the way, hodographs go up to 8 or 10 or 12 kilometers. I'm only showing you the lower part just to keep it simple right now. Okay. Now in this particular case, storm motion is shown as a red dot. In this case, 225 degrees at 30 knots. So again, 225 would be halfway between 180 and 270. So 225. So it would be along this radial and 30 knot circle here. So it would be from the center of the hodograph, an arrow that would look like this. And I've just not drawn the arrow, I've just shown you the dot showing storm motion. Okay. Now, remember that the winds that were actually plotted on the hodograph, like the surface wind here, which is from the east southeast at 40 knots, and the 1 kilometer wind, which is kind of from the due southeast at 50 knots, those are all ground relative winds. They're measured with respect to the fixed earth. Okay. So I think what you're maybe guessing we can do now is, with the two pieces, the ground relative wind, which is the absolute velocity, and the storm motion, which is the velocity of the coordinate system, the difference between these two is the storm relative wind vector. Okay, so there's a storm motion vector, 225 at 30, and the storm relative wind on a hodograph is found very easily by drawing the vectors back to the hodograph from the tip of the storm motion vector. In other words, what we're basically saying here is that the origin of the hodograph is shifted now from the center of the polar diagram to the tip of the storm motion vector. Okay, so in other words, in this particular case that I showed you, the storm relative wind, shown in this light blue color, can be determined at any level, not just the observation level, but at any point on the hodograph, by simply drawing an arrow back from the tip of the storm motion vector back to the hodograph. Okay? So, for example, at 1 kilometer, the ground relative winds are from the southeast at 50, okay, this vector right here, which isn't shown. Storm motion is the red vector, and so the storm relative wind from the tip of the storm motion vector drawn back to the 1 kilometer altitude, it's the storm relative winds are from what, like the east-southeast at, well, I don't know what the length would be. It would be, you know, I guess about 50 knots or so. Okay? So notice that the storm relative winds, how they change with height, okay, but we have to have the storm motion vector to determine what they are. So see how easy it is. Now we can find the storm relative winds if we know the storm motion and the environmental winds at any altitude. So for example here, or you notice this example here, we're finding the storm motion between two altitudes in which we actually have wind observations because the hodograph curve is continuous. Now do I know that the curve bulges out like that? No, I could have just as easily drawn a straight line, but the point here is that you draw the storm motion vector back to the hodograph curve from the, storm relative wind back to the hodograph curve from the tip of the storm motion vector. Okay? Now, the bottom line, of course, is, okay, so we can do this, that's great, but so what does that mean? Why do we even care? Well, we care because, for example, as I said before, in terms of dynamics, the storm relative winds are the only thing that really are important. They're the thing that matters. All right? So, there, with regard to storm dynamics, that's all that matters. In the case of supercell updraft rotation, now going back to that three-dimensional plot that I showed you on Tuesday, we want to see an alignment between the storm relative winds and the horizontal vorticity vector. Okay, you remember that? I showed you the storm relative winds were coming in the red arrow from the south. The horizontal vorticity vector was also pointing to the north. So we want those two things parallel so that when the winds were drawn up into the updraft, okay, they were automatically stretching the updraft. So we want the horizontal vorticity vector and the storm relative wind vector to be parallel. Okay, I won't pull up that PowerPoint slide, but if you go back and look at those two vectors, the storm relative wind vector was red, vorticity vector was blue, they were parallel to one another. Okay, and again, the alignment between those two is very easily determined on a hodograph. Okay, because remember, we just went over the storm relative wind vector, but remember the horizontal vorticity vector is at 90 degrees to the left of the shear vector at a given altitude. So we take the 0.2 kilometers altitude. What's the shear vector? It's pointing like this, parallel to my pin. Okay? So the horizontal vorticity vector is 90 degrees to the left of that. All right? Well, what you see here is now, in this case, at every level, almost a perfect alignment between the storm relative wind vectors in blue and the environmental horizontal vorticity vectors in red. Okay? And that's what we said we wanted, was that rough parallel alignment. Okay? Why? Well, here's that picture. Okay? Shear vectors like that. The horizontal vorticity vector 90 degrees to the left of the shear vector. In this case, we said, if we want to get stretching in the cyclonic member of this vortex pair, that is to create the mesocyclone, we want to shift the storm relative winds from the east over to the south. Okay, because if we do that, we have this this stretching immediately in the updraft of the cyclonic vortex. We'll notice that the storm relative wind vector and the horizontal vorticity vector are parallel. Okay, so that's kind of an optimal condition, and that is called, and I'll come back to this, but just you can write it down now. This is what's called streamwise vorticity, okay, or storm relative streamwise vorticity to be a little bit more accurate. In other words, the storm relative winds are blowing along the vorticity vector, parallel to the vorticity vector. Storm relative, streamwise, vorticity. Streamwise simply meaning the vorticity vector is pointing in the direction of the streaming flow, which is, in this case, the storm relative winds. Okay? Now, so click the mouse here, the wording changed. Note that the low pressure exists at the center of each of these vortices, and as I said before, those are lifting pressure gradients that cause air to rise from high to low pressure, because these are cyclostrophically balanced, not balanced, but they're roughly cyclostrophic vortexes. And they enhance the updraft beyond the buoyancy effects alone. Because remember I said there's two updrafts. There's the thermodynamic updraft, the buoyancy updraft due to latent heating. And these are dynamically driven because they have low pressure at their center. So dynamically they're drawing air upward from below. Okay? Now you're a forecaster, all right? And you're saying, okay, I see storms out there. I've got a thermodynamic sounding. I have a hodograph. are these storms going to exhibit rotating updrafts? That is, do they have the potential to produce supercell storms? Okay, well, through various studies, especially with numerical simulation models, we've come to a set of conditions that are most conducive for producing rotating updrafts and supercell storms. You need to know these, okay? So make sure that you study this slide. First of all, one ingredient. This is kind of a rule of thumb. Strong storm relative winds in the low levels. Now, what is low levels? Oh, from the surface to maybe 1, possibly up to 3 kilometers. Okay? So what that says is that through the depth of the atmosphere, typically shown here, anywhere from the surface to 3 kilometers, we want, on average, the storm relative winds to be at least 10 meters per second in length. All of these arrows individually, roughly 10 meters per second. Okay? Throughout the depth from the surface to 1, surface 2, surface 3, roughly in the lower part of the atmosphere. Overall, not just one level, but throughout the depth, averaging 10 meters per second. At least. Okay? Now, we also want strong turning of the wind shear vector with height. All right, now you have to be careful, and I'll show you why here in just a second. Turning of the wind shear vector with height. Remember what the wind shear vector is. It's tangent to the hodograph, right, at any altitude. So that means that the hodograph needs to have curvature. It needs to be a turning hodograph, and because then, of course, the wind shear vector turns with it as I go up in altitude. Strong turning of the wind shear vector with height, roughly at least 90 degrees through a right angle between the surface and 3 kilometers altitude. Okay, so if you go back to this hodograph, the wind shear vector at the surface is like that. The wind shear vector at 2 kilometers is like that. So this is that's a southerly and westerly, so that's a 90-degree turn. If I take it all the way to 3, it's almost like a 180-degree turn, from south to west to north. So 0, 90, 180 degrees. Okay, as I travel along the hodograph, the tangent to the curve is turning. Again, the shear vector always points toward increasing altitude, so you see it's turning through, in this case, about 180 degrees through 3 kilometers altitude. Okay, so one ingredient is strong storm relative winds, on average 10 meters per second throughout the lowest 1 to 3 kilometers. Strong turning of the wind shear vector. Now, folks, make sure you realize this is the shear vector. Circle the word shear. It is not strong turning of the wind vector. Okay? Okay, what is the wind vector? Remember, the ground relative wind vector is from the center of the polar diagram plot to the hodograph. Okay? So the origin here being the center of the polar diagram, that would be turning of the wind with height. And it does. It turns with height. The shear vector also turns with height. I'll show you a case a little bit later on where the winds change with height, but the shear vector does not turn with height. Okay? So we'll come back to that. Okay? The third ingredient we want is strong alignment between the storm relative wind vector and the horizontal vorticity vector. Why? To do what we've been talking about, to develop rotating updrafts. That is, to develop a preferential enhancement of the cyclonically rotating member of that vortex pair, so that the cyclonic member is preferentially enhanced. So we want to develop that, and so that requires, as I said before, the storm relative wind vector and the horizontal vorticity vector to be parallel, and that's what we mean by alignment. That you could say strong parallelism between those two vectors. Okay? So those three things, it turns out, can be quantified in a single quantity called the storm relative environmental helicity, or SREH for short. We oftentimes just abbreviate it SREH. Storm relative environmental helicity. Now, what is it? It's a measure of the potential for a thunderstorm updraft to rotate. Okay? Now, it turns out that it's a quantity that is actually measured over a depth of the atmosphere. Okay, it's measured throughout a particular depth. In this case, anywhere, it depends on what paper you read, but anywhere from 1 to 3 or 0 to 4 kilometers. Okay? Now, because helicity involves this notion of storm relative winds, I have to have storm motion, right? I have to have storm motion to get the storm relative winds. So a good estimate of the helicity, that is, of the potential for an updraft to rotate, depends upon a pretty decent estimate of the storm motion, as well as, of course, having, you know, accurate environmental winds, a good hodograph that's representative of the environment, but also good storm motion data. Now, how do I get storm motion? Like I said, if you have a storm that's already out there on radar, you can track it and get storm motion. You can also estimate storm motion even before a storm forms, and we'll talk about that a little bit later on from the hodograph. Okay? Now, let's see, let me show you in equation form what the helicity is. Okay, and I'll write this large. Okay, I'll just put this up there. The storm relative environmental helicity, SREH, maybe I ought to hold this closer so you can see it. It's coming through the backside. Hang on. Okay, there we go. Okay, the SREH is the integral from two levels. I'll just call it L1 to L2, excuse me, L1 to L2 of the vector storm relative wind. I'll call it V sub SR, V sub SR, the storm relative wind vector, dotted with, you could call this omega sub H. Let me write omega sub H on there. That is the horizontal vorticity vector, omega sub H, dz, integrated over a depth. So in other words, it's basically the cosine, proportional to the cosine of the angle between, if you take the dot product there, the storm relative wind speed, excuse me, the storm relative wind vector and the horizontal vorticity vector, integrated over some altitude. Okay, that's what's called the storm relative environmental helicity. Now you're going to show in a problem set that this has a very, very simple graphical interpretation on a hodograph. So let me tell you what that graphical interpretation is, and then I'll show it to you schematically. Okay, it's a little bit complicated sounding, but in practice it's very simple, as you'll see. It's the area, so it's actually minus twice the signed area swept out by the storm relative winds between the surface, or, you know, typically we look at the surface, and either 1 to 2 or maybe even 3 kilometers. Okay? It includes all the ingredients that I mentioned earlier. The alignment of the storm relative winds, okay? The strength of the storm relative winds being roughly 10 meters per second throughout the depth of whatever we're calculating here, for example, 0 to 3 kilometers. And also a significant turning of the wind shear vector with height. So it includes all three of those ingredients in one simple quantity. Okay? So here's how we get the storm relative helicity on a hodograph. So here's our hodograph. Curve is shown with the yellow curve. The altitudes are labeled. All right? Storm motion is shown here in this green arrow. And so the storm relative winds at the surface are shown, I don't have it drawn as a vector arrow, but as shown here. Storm relative wind vector there. We're doing this between 0 and 3 kilometers. So there's the surface. 3 kilometers is like this. So if I shade the area swept out between the 0, the surface, and the 3 kilometer storm relative wind vectors in the hodograph, that kind of creates an area here. If I shade that in, that represents, it should say not the 1 to 3 kilometer helicity, is 0. Change that to 0. Let me do that now. Sorry about that. It should be the, I don't want to get you confused here. Do a little real-time editing here. Okay. That should say the surface of the 0 to 3 kilometer helicity. That's the area. Okay? Now, it turns out that this thing has a quantity of energy, of kinetic energy, meters squared per second squared. Because you go back to the definition of that integral I gave you, V dot omega, okay, V dot omega dz, V is meters per second, omega is 1 over seconds, and z is meters, so it's meters squared per second squared. So it has the units of energy. Okay, now Bob Davies-Jones at the Severe Storms Lab did a study and looked at the various thresholds for potentially tornado intensity. What he found was that if you have storm relative environmental helicities of 150 to 300, you could have potentially weak tornadoes, 300 to 500 strong, and greater than 450 meters squared per second squared, you could have violent tornadoes. Okay, now what do we mean when the numbers get larger? What does that mean? Okay, well, we'll look at that here in just a second, and I'll kind of give you a real-time quiz here to see if you can come up with the best situation for, say, a strong tornadic storm. Okay, so that's how you get helicity. Now again, helicity can be computed, and typically when you see a real sounding, in fact, let me jump all the way. You don't have, well, yeah, you can go in your notes back here, but let me just show you a real hodograph. There we go. Let me zoom in there. Why is it not focusing? It should focus better than that. Let me see here. I'm not sure why it's not focusing. This is a new camera, and I'm still getting used to it. Well, anyway, let me pull back just a little bit. Maybe that'll help. There. You've seen these soundings before. I know you probably can't read this, but it says here storm relative helicity 45. Now this is a winter sounding. Storm relative helicity 45 meters squared per second squared. Okay, so it actually computes the helicity for you, and I'll show you here a little bit later on. So the point here is that helicity has numbers with it, right? You can actually compute it, but on a hodograph, typically all we're really interested in is eyeballing it, as you'll see here a little bit later on, and then you can look at the numbers as they're computed and provided, say, on a sounding like I just showed you. Okay. Okay, so let's look at go back to our very simple classification for storms. Say a single cell hodograph would look like this. If we plotted up a typical sounding from sort of ordinary cells, you see that there's weak shear and weak winds. This is the radius of the hodograph here. You notice that if storm motion vector is like this, okay, and I look at the helicity, it's going to be really small, right? Because if I say from the surface, you can't even find it. The surface is sort of right here, 4 kilometers here. There's almost no area swept out at all there. Okay, so you see that single cell storms form in environments with almost no helicity, so you're not going to expect the updraft to rotate. Okay, now typical multi-cell hodograph, where you would say, for example, have cell motion and storm system motion. We saw earlier how those could be different. We have stronger winds. Interestingly enough, the hodograph is kind of straight, especially down at low levels. Okay, so if I say just look at the storm system motion overall, well, actually no, let's take cell motion. Okay, because that would be the motion of a given updraft. Let's draw the storm motion vector back from the cell motion back to the hodograph at 1 kilometer, 2 kilometer, 4 kilometer altitude. The storm relative winds are like this at the surface, or 1 rather, at 2 and at 4. So notice that the storm relative wind vectors are like this, but the horizontal vorticity vectors are like this, right? 90 degrees to the left of the shear vector. So they're almost perpendicular. Well, what did we say we wanted for strong rotating updrafts? We wanted alignment of the storm motion, the cell motion, and the horizontal vorticity vector. Well, there's almost none. In fact, if you think about the helicity, what's the area swept out between this wind vector, say between 1 and 2? It's almost nothing. There's almost no area at all. So this has very, very weak helicity. Okay. Now, typical supercell hodograph that you see here, these are kind of canonical examples. Okay, suppose we have storm motion vector like this. Notice how the shear vector turns with height, right? You can see the shear vector turning with height. Storm motion is here, so let's look at the storm relative winds. Okay, at the surface they're pointing like that at 1 kilometer, at 2 kilometer altitude, at 3, at 4, like that. And so just eyeballing this, you could say, well, the helicity between surface and 3 looks like it's a pretty good area right in here, right? Okay, and are the storm relative winds greater than 10 meters per second throughout that whole depth? Yeah, absolutely. Okay, assuming this is meters per second, right? Storm motion, vector, this is 10 meters per second, so sure enough, yeah, the storm relative winds would be, that'd be the 10 meter per second value is here, and it doesn't even touch the hodograph. So sure enough, we have extremely strong storm relative winds, the shear vector turns through 90 degrees, so the helicity here appears to be pretty substantial, and sure enough, you would expect to see a supercell storm. Okay? So let me give you a little quiz here as we're going through this sort of in real time, and ask you, based on this green hodograph that we've been looking at, okay, and I've got these various storm motion vectors here, 1, 2, 3, 4 storm motion vectors. Which one of those storm motion vectors produces or would be likely to produce a cyclonically rotating supercell, and why? So let's go through them one by one. Let's see. I'm trying to think of... Okay, I think I did this, yeah. I am doing this one by one. So we have 4 different storm motion vectors. So remember, estimating the potential for updraft rotation. What are the 3 ingredients? Strong storm relative winds in the lowest levels, roughly 0 to 3 kilometers. Strong turning of the shear vector through 90 degrees, roughly through the surface to 3 kilometers. And strong alignment between the storm relative wind vectors and the horizontal vorticity vectors, again, through the same depth, 0 to 3 kilometers, roughly. Okay? All right? So let's pick this particular storm motion over here. There are 4 of them. Let's just look at this one right now. Okay? Let's look at the alignment, first of all, the storm relative winds and the horizontal vorticity vectors. Storm relative winds I've drawn in blue here, right? So the storm relative winds between that storm motion and the surface are really tiny. At 1, they're like this. At 2, they're like this. At 3, they're like this. So is there good alignment between the storm relative winds and the horizontal vorticity? Well, at the surface in 1 kilometer alignment, forget it. They're almost perpendicular, right? Here in red is a horizontal vorticity vector, right? 90 degrees to the left of the shear vector. Here's a shear vector turning with height. Vorticity vector is pointed 90 degrees to the left of that. And the storm relative wind vector you see in blue here is almost perpendicular to that. Now, at 2 kilometers, it's not too bad. Okay, the storm relative wind is like this, vorticity is like this. But it's still not as good as it could be. Now, at 3 kilometers, it's perfect, right? It's huge, strong storm relative wind speed. Okay, almost perfectly aligned there. But notice that the wind speeds, the storm relative winds down here are just roughly at 10 meters per second. Okay, so do we have strong alignment? No, not really. Certainly through the surface to 2 kilometers, we don't really have strong alignment. Only at higher altitudes do we. So we really want that through the lowest part of the troposphere, 0 to 1 to 2, maybe up to 3. But if it's not happening low down, then even though it's happening up here, we really need it to happen low down. So no, we don't really have good alignment there. Okay? What is the storm relative environmental helicity? It might be pretty big, actually. Okay? What is it? It's the area swept out, right, between the storm relative winds and the hodograph, storm relative wind vectors and hodograph between the surface and 3 kilometers. So it's that area. So would you expect a strong supercell? Probably not. You got good helicity, but you don't have decent alignment of the vorticity vector and the storm relative wind vector down low. Okay? Now let's go to the next storm motion up here. Okay? So here's the storm motion. The storm relative winds, remember, are the vectors drawn back from that storm motion to the surface. To 1 kilometer, you can't quite see it. It's right on top of the surface. So the surface is a long one. There's the 1 to 1 kilometer to 2 to 3. All right? What's the alignment between the storm relative winds and the vorticity? It's horrible. Here it's almost perpendicular. Here it's almost perpendicular. Here it's almost perpendicular. Here it's not perpendicular, but it sure isn't perfectly parallel. So it's pretty awful there. Okay, so the alignment's quite bad. All right? Before I jump to that one, let me say, what is the horizontal vorticity here? Excuse me, sorry. What is the helicity? The helicity here is actually negative. Okay? When we're measuring the helicity, let's see, let me go back to a different picture. Okay? It's minus, well, let me just say, the helicity is positive if it's measured with the hodograph turning clockwise. Okay, like that. In the case that I've shown you here, when I measure when I go with the storm motion back here, and I go to higher altitudes, what do I get? Okay, from here to here, the thing is turning counterclockwise, and then it's a little bit clockwise here. So what I'm saying here is that it's the area swept out between these storm motion vectors and the hodograph. Well, this whole area is this area. It's on the convex side of the hodograph, and that's all negative, and then you bring in some positive here. So the helicity here is quite small. If anything, you're going to get an anticyclonically rotating updraft here, because you don't have parallel alignment between the storm relative wind. Well, in fact, I shouldn't say that. You probably will get no rotation there, or very little. Let me just leave it at that. Okay, very little rotation there. Very little significant rotation. Now, how about this storm motion over here? Okay, let's again draw the storm motion vectors back to the hodograph. And what do you see? You see 10 meters per second throughout the depth of 0 to 3. Yeah, you sure do. Very, very strong storm relative winds. And notice that roughly the storm relative wind vector is roughly parallel to the horizontal vorticity vector at each of those 4 altitudes. So this is, if you look at the helicity, this is a very, very strongly helical environment, as we say. Strong turning of the shear vector, strong storm relative winds, very large area swept out between the storm relative wind vector between the surface and 3 kilometers and the hodograph curve, so a very, very large area. You would probably get a very, very strongly rotating, cyclonically rotating supercell storm in that case. Okay. Now, how about this guy here? Okay. Surely you have very, very strong storm relative winds from roughly the surface up to 1 kilometer altitude. The alignment of the vorticity is not bad. It's horrible at 2. It's almost perpendicular, plus the storm relative winds are weak there. But if you look overall at the helicity, do I have a picture of the helicity? Yeah. The helicity is here. So the helicity is not huge, and you may actually get some type of rotation there, but it certainly would not be anywhere close to the type of rotation you would get here. Okay. So the point I want to make from this exercise is that notice how the helicity is a function of storm motion. Okay? The hodograph didn't change. We were looking at the same hodograph the whole time, right? But the thing that changed in each of these examples was the storm motion. And of course, you know, what we're saying is, I should be more precise, it's the motion of the updraft is what matters. Okay? We talk about it being a storm, but what is rotating is the updraft. Okay, so dynamically, we care about the updraft, and the air coming into the updraft is the vorticity streamwise and so on. That's what we care about as far as updraft rotation goes. It's not the storm rotation, or storm motion, it's the updraft rotation and updraft motion. Well, typically it's hard to know where the updraft is with a single Doppler weather radar, so you're kind of looking at the cell and how the cell is moving. But you see how the different storm motions here can provide different types of rotation, different degrees of rotation, different potential intensity for a supercell storm. Okay. Now let's kind of play the game a little bit further here and say, suppose we have a hodograph that looks like this. Now this has a particular name associated with it, other than the fact that it's a straight hodograph, but it's called unidirectional shear. Okay. The interesting thing about this hodograph is, so it's unidirectional shear. The ground relative winds change with height, but the shear vector does not. Oops. Okay, so what are the ground relative winds? Bump the camera. The ground relative winds from the surface are about, from, I don't know, 110 degrees at 52 knots or whatever. 1 kilometer is like, say, from, what is that, 135 degrees at 40 knots, at 2 kilometers like this, 3 is like this. So notice that the ground relative winds, again, drawn from the origin of the plot here out to the hodograph, that's the ground relative wind, and it definitely veers with height. Okay, but remember, the shear vector is tangent to the hodograph curve pointing toward higher altitude. So at every level, the shear vector here points in the same direction like this. Surface points there, 1, 2, 3, it all points the same. So we call this a unidirectional shear profile. It's not a unidirectional wind profile. The winds are varying with height, but the shear vector is not changing with height. Okay, and this is why I pounded home the point earlier with the curved hodograph to say, make sure and differentiate between the winds turning with height and the shear vector turning with height. In this case, the wind vector turns with height, but the shear vector does not. It's unidirectional. Okay? Well, the horizontal vorticity vectors, remember, are everywhere perpendicular and oriented 90 degrees to the left of the shear vector. So that's what the horizontal vorticity vectors look like. Okay, we've seen that before. So, suppose you have a little red dot here, and I'd say, all right, place that dot to give me a storm motion that will get us the strongest cyclonically rotating supercell storm. Where would you put it? Where would you put the dot? Okay? Would you put it there? Where would you put it? Well, actually, where it's at right now is actually pretty good. It's unrealistic, okay? But suppose storm motion were down here. Storm relative winds would be drawn from there back to the hodograph, right? So yeah, you know, you're talking storm relative winds of 100 knots at every altitude. That's sort of silly. But you do see, if you do that, tremendous alignment between the between the storm relative wind vector at each of those altitudes, right? Drawn from the storm motion vector back to the hodograph. Almost perfect parallel alignment between the storm relative wind vector and the horizontal vorticity vector. Do you have turning of the shear vector with height? No, but you have pretty high helicity, right? The helicity would be, you know, it'd be this triangle here. Okay, the helicity would be this whole big triangle area. So that's a huge amount of helicity, but no turning of the shear vector with height. Now remember I said we have to have turning of the shear vector through 90 degrees. All right? Why do we not seem to have that here? Well, it's because the storm motion I gave you is unrealistically large. You'd never see it that large. You'd more typically see a storm motion vector up like this. Okay? So if that's the case, you might not really get a strongly rotating supercell. Okay, so I might ask you on an exam, what happens if I put the storm motion vector up here? Suppose the storm motion vector were where my finger is pointing. What type of updraft would I actually get there? In what sense would it rotate? Okay, let's go through the ingredients. Suppose the storm motion vector is where this S is, all right? So the storm relative winds are drawn back to the hodograph from that tip of that vector. So the storm relative winds are certainly bigger than 10 meters per second is 20 knots, and it's certainly bigger than that at every level. Notice how the storm relative wind vector is now, is it parallel to the horizontal vorticity vector? No. It's anti-parallel, okay? Especially, it's say like here, it's almost perfectly anti-parallel. Here a little bit more. Almost perfectly anti-parallel. What does that mean? Well, if I go all the way back to the previous slide, that says that the storm relative winds, maybe I ought to do that. It's going to take me a second to get there. Whoops. If the storm relative wind vector is not parallel to the vorticity vector but anti-parallel, suppose the storm relative wind vector is like this. Okay? So that it opposes the vorticity vector. When that air gets lifted into the updraft, what's it going to do? It's going to stretch the anticyclonic vortex. Okay? And it's going to create a strong anticyclonic storm. So we'd have a meso-anticyclone in that case. Why? Because the storm relative wind vector is anti-parallel to the vorticity vector. I can still stretch that vortex. It doesn't matter the sign of the vorticity. If I have stretching in there, I can stretch that vortex. All right? Go look at the vorticity equation. If the vorticity is negative, and I'm increasing it to be more negative, I can just as easily stretch that vortex and make it a anticyclonically rotating supercell. So in that case, the left moving storm would maybe survive, and the right moving storm would die. Okay? So that would be a storm motion vector here. So you need to know that. I'm going to ask you this on a test. I'm going to give you some hodographs and ask you to determine which storm motion vectors that I give you are likely to produce the strongest cyclonically rotating storm, anticyclonically rotating updraft, so on and so forth. And so you're going to, again, look at whether the storm relative wind vector is parallel or anti-parallel to the horizontal vorticity vector. You're going to look at the helicity. In this case, notice what the helicity is. Okay, from the surface to 3 kilometers, what direction is it going? It's going anti-clockwise. So it would be this triangle right here. But it's negative because as I go from the tip of the storm motion vector, surface up to 3 kilometers, this thing is rotating not clockwise, but anti-clockwise, counterclockwise. Whereas over here, let me give this example. Okay, from the surface up here, it's rotating clockwise. So the area here is swept out clockwise. The area here is swept out counterclockwise, and it makes it negative. So negative helicity could still produce a mesocyclone, but it's going to produce a meso-anticyclone, not a mesocyclonically rotating vortex. Okay? So one way we can sort of make an optimal hodograph, so to speak, is, actually it's not making an optimal hodograph, it's it's optimizing the ability of a storm to become a supercell. We do that by looking at different possible storm motions. So as a forecaster, you might say, okay, on a given day, and I'll show you this in a picture later on, I think it's in the PowerPoint here, that where you can actually, in fact, let me see real quickly if it is. If it's not, I need to go dig it out. It's not. Okay, I need to go get that. And I will do that. I'll tell you what I'm... let's see, let me just put this back up where we had it. The point here is that if I have a hodograph in a given day, I can estimate or guesstimate what the storm motion might be on a given day. And if it turns out that the storm motion is a particular value, then I would know immediately that I would potentially have a strongly rotating storm. Okay, I have published a paper actually back in 1993 on this in it was Monthly Weather Review. It's the July issue of Monthly Weather Review. I'm going to try to show you this picture. I thought I had it in the PowerPoint, but I don't. This is from a journal article. Let me try to bring this up here. Okay, so what you see here is it's an idealized hodograph. It's a half circle, and we use these in numerical simulations. Let me try to hold that still. Okay. Notice those horizontal or those diagonal solid lines. Those are contoured with values of helicity. You read those? 100 in the upper left, 200 down below, 300, 400 as you go from upper left to lower left. Okay? So it turns out that on a hodograph plot, the helicity contours for a given hodograph, in this case anyway, because it was an idealized half circle, are straight lines. So what I can do is say, okay, from there, that picture, if I read off what the storm motion is, sorry about this, it's kind of jumping around. If a storm is moving like this, I can read off the diagram, it has a helicity of about, I don't know, 260 or something. If it's moving here or over here, notice how the helicity gets bigger. Well, why does it do that? Because the storm relative winds are roughly parallel to the horizontal environmental vorticity vector. Okay, see how neat that is? So if you go up here close to the hodograph, look at the values of helicity. They're small, like 100 in here. So the further away I go, the larger they get. Well, why is that? It's because the storm relative wind vectors tend to be aligned more with the horizontal environmental vorticity vectors. Okay? If you want to see this plot and look at it a little bit more in this paper, this is the title of the paper called The Influence of Helicity on Numerically Simulated Convective Storms. It's Monthly Weather Review, Volume 121, July 1993, and the article starts on page 2006. So July 1993, Monthly Weather Review 2006 is the starting page number, and that was figure 10 that I just showed you. And so the point is that, you can see there that if you have wind profiles that are fairly idealized like that, and even if you don't, the computer program can actually plot contours of the helicity for a given storm motion. So it makes it very nice and easy to see the relationship between storm motion and helicity. Okay, now suppose we say, all right, we have this hodograph, and we've also got a storm motion fixed. Okay? Let's just suppose that for whatever reason a storm motion is there. What kind of a storm are we likely to get? Well, if you look at the storm relative environmental winds, yeah, they're about 20 knots throughout the whole depth, so that criterion is pretty well met. It's actually fairly parallel, that is, the storm relative environmental wind vector is fairly parallel to the horizontal environmental vorticity vectors here, but it probably could be a little bit better. Okay, the question is now, how would you actually change the shape of the hodograph to obtain a stronger storm, and certainly a strong rotating supercell, if you had the opportunity to just magically draw the hodograph? Okay, so I'm not saying in practice you can do this, but you might as a forecaster say, well, I expect the low-level winds to do something to change over time, and if they do, and storm motion stays roughly the same, we might see a change in the character of the storms that would form. Okay, so how might you change the hodograph? Well, change in what sense? Change to produce a greater degree of alignment between the storm relative wind vector in blue and the environmental vorticity vector in red. And you can't change storm motion, you have to change the hodograph. How are you going to do it? Well, one way to do it would be to put a little tail on the hodograph. So sort of get rid of this part here and assume that the winds now, instead of being from the southeast, they're more from, say, the due east or a little bit east-northeast, okay, and then turning like this. So you have the ground relative winds doing this kind of thing. Why would you want to do that? Well, because you increase the intensity. You increase the intensity of storm relative winds, but notice that the horizontal vorticity vector now at this level is like this. At this level, it's like this. So you get almost perfect alignment of the, or a much better alignment between the storm relative wind vector at the surface in 1 kilometer and the horizontal environmental vorticity vector. So if you draw the environmental vorticity vector out from the hodograph, of course, here it would point like this. It would be red pointing like that. Here it would be red pointing like this. And those would be almost parallel to the storm relative wind vectors. Okay, then as you continue upward, it's pretty darn good at 2 kilometers. So drawing a little tail like that would certainly give you an improved probability of rotation because you have this greater alignment. Well, it's no surprise then, if I go back to this earlier picture for supercells, that this actually is a lot of hodographs, I think averaged over a lot of different cases. You tend to see a little tail on the hodograph, sort of the canonical, typical, classic supercell storm. So you tend to see maybe sort of a unidirectional shear up above, but the hodograph has a distinct tail here. Why is that? It's because that type of an environment is conducive to supercells with storm motion here, because I get extremely good alignment, good helicity in the low levels. So that's just an example of why tornadic supercell hodographs tend to look like that. Okay. Now, all of that stuff on helicity, okay, and streamwise vorticity we talked about, predicted the sense of updraft rotation, cyclonic or anticyclonic, and the potential to produce strong mesocyclones and tornadoes. Okay, so it said nothing about storm type. If you go back to that picture I showed you with the threshold values from the Davies-Jones paper of strong, violent tornadoes and weak tornadoes and so on, that was helicity. It was the intensity of the rotating updraft and the mesocyclone and the tornado. Okay, that's what the helicity is really good for. Now, if we want to look at thunderstorm type, and this is a bit of a review now, when we talk about type, that's where the Bulk-Richardson number really has value. Okay, remember the Bulk-Richardson number is the ratio between the CAPE, the integral of the buoyancy over the positive area on a hodograph, divided by a measure of the environmental shear, which in the case of how the Bulk-Richardson number was defined in the literature was the difference between the 6 kilometer and the 500 meter wind squared and half of that. Okay, so it's not even, all it is speed shear. It says nothing about direction. Okay, so the point of the Bulk-Richardson number is to get supercells you need sufficiently large CAPE. Okay, the denominator, as I said before, is kind of the storm relative inflow kinetic energy, called the BRN shear. So it's a measure, this is a measure of the inflow kinetic energy versus the potential energy of the updraft. Okay, so BRN is a measure of the updraft potential versus the inflow potential energy, and really is more of a classification of storm type than anything else. Okay, and as I showed you before, we tend to get, do I have the thresholds? Yeah. Let me go to this first. Supercells for BRN between 5 and say 50, and then kind of an ambiguous region where you have, say, between 50 and 35, you could have supercells or multicells, and multicells between 35 and 400. Okay, in this picture I won't, it probably doesn't show up too well on the screen there, but these are actually observed storms, supercells in here with splitting, secondary storms. These are kind of tropical multicells and multicells over here. So clearly the supercells tend to fall in a region from say 10 to roughly 50, and then multicells are above roughly 50. Okay, and it works pretty well. It's really quite amazing how well it works. The interesting thing about the Bulk-Richardson number, though, because it does not take into account the wind direction, this U bar doesn't necessarily mean the east-west wind. It means the wind speed at 6,000 and the wind speed at 500, the difference between those two things. Okay, so it's really looking at speed shear, not directional shear. Now remember, in the helicity, it was all about directional shear. It was looking at how the shear vector turned with height. Okay, So two very, very different quantities. Helicity is really for determining potential of updraft rotation, whereas Volk-Richardson number is really looking at storm type. Okay. Now you would expect, presumably, that if you had a small BRN, say like 25, the lower it is, the more likelihood you'll have for strong updraft rotation, and that's true. But the BRN cannot tell you whether the updraft will rotate cyclonically or anticyclonically. The helicity can. In the example I just showed you, I argued that it would be an anticyclonically rotating updraft because the storm relative wind vectors over the layer 0 to 3 kilometers was roughly anti-parallel to the vorticity vector. The BRN doesn't do any of that. Okay, it doesn't distinguish the vector shear, the turning of the wind with height, or any of that. All it is a ratio between is the cape and the shear magnitude. Okay, so the bottom line point here really is that you have to use the Volk-Richardson number and the helicity together. Okay, and I actually had a master's student that did a wonderful piece of work looking at this very point of the BRN and the helicity and how useful they were separately or together. And we actually never published it, unfortunately, but it was a very good study. If you're interested, I'll be happy to tell you about that. Okay, now we've talked about what happens if we get storm relative winds coming into the inflow on the south side of a storm parallel to the environmental vorticity vector. We talked about the preferential enhancement of the cyclonically rotating member of that split vortex pair. Okay, but we had never said what would cause a storm to do that. What would cause a storm to turn to the right so that the inflow would be from the south rather than from the east. Okay, and that's what we're going to talk about now. Selective enhancement and deviate motion of right-moving storms. In other words, it's a fancy way of saying, why do storms tend to turn to the right? What turns them? Why do they do that? Now, it's you know, if you like supercells, it's a good thing that they do, because when they slow down and turn to the right, you can expect them to really intensify and wrap up and increase their updraft rotation pretty dramatically. But what causes them to turn in the first place? Okay, so let's look first at a very simple case, a purely straight hodograph we saw before, where the shear is unidirectional, with westerly winds increasing in speed with height, and there are no north-south wind present. This is basically the same thing we've been looking at all along. Kind of forget the north-south wind, just make it simple, an east-west shear. Okay, and an incipient supercell, in that case, will form mirror images of left and right moving members. So what do I mean by that? I mean that if we have a straight hodograph here, okay, so 0 to 5 kilometers is what's shown. So here's the hodograph. So just only look at the red part. And this is in a numerical simulation now. We trigger a storm in the numerical simulation. What happens? It splits. Okay. And what essentially happens in the split is, and I have a movie of this. I need to dig it out and show it to you. But essentially what happens is the updraft gets cut off by the downdraft and splits into two pieces. And if you have no Coriolis force in the simulation, you just turn it off, then there's nothing that will bias the left and the right sides. Okay. Now, if we had Coriolis turned on, then the storm to the north should preferentially rotate cyclonically, right? Because F is bigger over here, so it ought to add to the vorticity or weaken it, because this is an anticyclonically rotating storm and this is cyclonic. So you actually ought to see the left mover weaken. If you turn the Coriolis force off, what you get after the elongation and the split are two mirror image storms moving off like this. Okay, the updraft here is cyclonically rotating, the updraft here anticyclonically rotating, and they're mirror images of one another. That's what you get for the straight hodograph case. Okay, now the storms typically move, when you start the simulation, they're moving with the wind itself. So they might be moving somewhere here close to the hodograph or along the hodograph. But when they split, you get the left mover here and the right mover here. Okay, you see those two dots. You can probably see them in your plot where it says L and R. That's the left and the right moving storm. Well, you look at the right moving storm, okay, and its helicity, okay, it's positive helicity. The left moving storm is a mirror image, it's negative helicity. So the left moving storm is ingesting flow from the north, right? Okay, the vorticity vector in this plot in the hodograph is everywhere pointing toward the north. So vorticity vectors like this, the storm relative winds are like this, are anti-parallel. So the anticyclonic updraft in the left mover is going to be enhanced, whereas in the right mover it's just the opposite. We have the storm relative winds from the south, the environmental vorticity vectors from the south, so we're going to get a strong cyclonically rotating updraft in the right moving case. Okay. Now, it was studied back in the late 70s. Actually, my doctoral advisor, Bob Wilhelmsen, at the University of Illinois, working with Joe Klemp at NCAR, kind of discovered this behavior that I'm going to show you in numerical simulations, but they couldn't really explain it, at least not dynamically. What they found, though, was, when you have a straight hodograph, you get this nice symmetrically split pair of storms. But now, it turns out that if I add curvature to the hodograph, the southern member of that split tear tends to be the strongest. It also tends to slow down and travel to the right of the mean wind. Okay, so in a simulation where we do the same thing now, we're going to take the straight hodograph and we're going to add a tail on it, like we saw before. Okay? Now, notice one important thing here. The left and right mover, the storm motion here, is both these storm motions are on the concave side of the hodograph. Whereas up here, the left mover was on, well, of course, there's no concave or convex, but the point is that this had negative helicity and this had positive helicity. Here, both of these storms have positive helicity, right? Because the storm relative winds drawn back from the left mover look like this, from the right mover just are bigger, roughly. So they both have positive helicity. Well, what happens because of that is you get the split. Notice two things. There's asymmetry, right? The updraft of the right moving member is stronger than the left, and eventually the left dies out, and the right moving member produces a very strong updraft and a very pronounced hook, cyclonically rotating mesocyclone, and it becomes the dominant storm. Okay? So the point is, why in the world is that happening? What is causing the left mover to preferentially die off, and the right mover, notice how the storm here is turning to the right. Okay, the mean wind is like this. It's turning to the right and it's slowing down. And it's also developing a very, very strongly rotating updraft. Why is that happening? Okay. Well, it was hypothesized back in the 60s that this sort of deviate motion, that is the tendency of a storm of the right moving storm, and this notion of splitting storms has been noticed for a long time, and frequently in the northern hemisphere, in the mid-latitudes, you would see the right moving storm become a very strong one, left mover die out. Well, various people tried to explain that. And here's one theory that was disproved. Okay, this is sort of an obstacle flow analogy. Okay, let me explain this picture to you. Okay, the low-level winds. This is sort of a standard direction here. East is to the right, and north is in perspective in this direction. Okay, so what you see here at low levels, these wind vectors, that's a southerly wind. Let me see if I can zoom in just a little bit there. So you see the southerly winds here at low levels, V sub L. VU is the upper level wind, which is from the west. So we have a typical, veering of the wind with height, maybe increasing in speed. That's fine. Okay. The storm motion is the dashed line that you see in here. So the storm is kind of moving to the northeast. Okay. Now, if you look at the low-level wind here, you look at the storm motion vector, then the relative wind relative to the storm motion is actually this double lined arrow here. So in other words, the strongest inflow is coming in here from the southeast. Okay? And the strongest outflow is coming from the northwest up aloft. Now, it was hypothesized that you have strong convergence down here, right? Because the relative inflow is like this, strong rising motion. You see the tower here, these towers, and strong divergence aloft. So what was hypothesized was that you were getting new development here on the forward right flank of the storm. So you're getting new clouds developing here and stuff, and essentially, much like a multi-cell storm, this thing by discrete propagation was growing on its southeast side. So it was moving more toward the south, so it was sort of turning to the right in the sense that it was growing on the right side. So it wasn't so much turning; it was growing by discrete propagation. More the storm was growing here; it was kind of dying on the north, so it was kind of growing its way more to the east and the south, and that's what was believed to be responsible for that deviate motion. Okay. It turns out that that's not right. That theory has since been disproved, and I'll show you an example of that here in a second. Okay. Another effect that was proposed to explain this deviate motion, turning to the right, was something that Fujita had, I think, originally proposed, and that Chester Newton and I think it was Bob Fankhauser put forth in a journal article in 1964. And it was called the Magnus effect. And the idea here, it's very much like a baseball, okay, in terms of throwing a curveball. For whatever reason, okay, the storm updraft is rotating. So given storm updraft is rotating, given we have them as a cyclone, so it's rotating cyclonically, all right? If you put that updraft in a flow from left to right, so these arrows show the environmental flow, and again, the updraft is not a porous object, okay, but assuming that the flow kind of goes around it there, okay, what you see is an enhancement of the left to right flow here because the environmental flow is added to the direction of rotation of the updraft. So the winds here are blowing much more strongly from west to east, whereas up here, the environmental flow is still west to east, but it's opposing the flow of the updraft. So it's going like this, the updraft flow is going like this, and they oppose one another. So you get a very strong flow here and a much weaker flow here. Well, we know from Bernoulli's equation, right, that where the flow is fast, the pressure is low, right, following a streamline. So what you would get is a high to low pressure gradient force acting across the updraft that would, they believe, because the updraft is rotating, would give a deviate motion to the south. The high to low acts laterally across the updraft, which would sort of, cause the updraft. That's a force, so it would accelerate the updraft to move more in a southerly direction. So it's already moving east, right, due to the upper level winds, or mid and upper level winds. So the high to low pressure gradient force would cause it to not move west to east, but to turn to the south. So it'd have sort of a northwesterly motion from northwest to southeast. That theory, too, was also proven to not be the case. Kind of an interesting theory. It's how throwing a curveball works in baseball, and that is true in baseball. That's why it works. But in the case of storms, storm is not a solid object like a baseball, so it doesn't work. Okay. So there is theory of an isolated updraft, and we're going to use linear theory. And honestly, I think at this point, even though we have about 10 minutes left in class, I'm going to stop here because even though I will be here next week to continue this lecture, and I'd rather do this in person because we're going to be deriving some equations and stuff. So let's go ahead and stop here. And let me ask that you go in and again to the reading assignment in Howie's book and other things that you look at the assignment on the theory of an isolated updraft. Okay, that you read the material that's in the book on the theory of an isolated updraft. Okay, and make sure that you're reading the material on helicity and so on in that handout that is, just so you know, it's the handout that is 44 pages long. Okay, and it's printed out in the landscape direction, not the portrait, but the landscape direction. So make sure that you look at that. Okay. All right, sounds good. Well, I will see you all next Tuesday. I will be in class, and I will see you then.